Welcome back to Tailored Materials. We're going to have a look at the surfaces of materials now. I'm going to put some more light on. Okay, that's better. A bit more light, then you can see me and I can see everything. Just checking everything is working. Surfaces today. So if we look at a material that you've been thinking of in metallic materials or in non-metallic materials, you would be thinking of it in an engineering manner, where the material is a continuum. This isn't particularly engineering-y, because also in chemistry we would think of a solution typically as being a continuum most of the time, and then some of the time we would think about the molecules. The same is true in engineering. So if we use a material to make something like a pen, most of the properties that we're interested in are the stiffness and the toughness and whatever else we might be interested in, conductivity, maybe thermal conductivity, any properties that we would usually use are bulk properties, so we would imagine it to be a continuum. Likewise in physics, when you've considered bodies, you would be considering them to be a generally boring continuum. But at the surface, something new happens. So if we go to your metallic materials, we would be imagining that there are some kind of particles in here. And those particles are in some kind of array, because it might be a crystal. Even if it's not a crystal, there will be an average separation between particles. So if we take something that's completely amorphous, the next atom is somewhere around it, about 1 and a bit atoms away. That's all fine. Even if we look at a liquid, so let's take a liquid, take some water for example. We've got our water molecules, which are shaped like little gulls. So this is the oxygen, the two ends of the hydrogens, and in a normal configuration, they will be whizzing around as a liquid, because normally we're at 20-25 degrees centigrade, that is. The easy way for them to join together, there are two easy ways for them to join together, is like cups that you might stack in that weird sport. Like cups because the dipoles line up. Or alternatively, they might line up in a tetrahedral fashion to do more hydrogen bonding. If it turns into a solid, then they have to move to a better position for that. But as a liquid, they're doing something in between. There's sometimes hydrogen bonding, there's sometimes dipole interacting. So every molecule of water is interacting with molecules all around it. And that makes it happy. In anthropomorphizing chemicals, happy. It's surrounded by other water molecules, and they are most of the time interacting positively with it. So most of the time the dipoles are pointing in a good direction. Most of the time there are electrons being fed into the electron poor regions and electrons being pulled out of the electron rich regions, which lowers the global energy of the system, and the molecule is relatively happy. But this molecule up here on the surface of the water doesn't have any of that. Or at least it does have it downwards, but it doesn't have any upwards. And so it is a special molecule. Half of its space is not the same as the other half. Half of the space is water and it's happy down there, and half of the space is air, and water particularly is less happy in air. All of those good things, dipole interactions, hydrogen bonding, van der Waals interactions as well, aren't happening out here because there aren't very many molecules in the air compared to in the water. There's pretty much none. In fact, the density of air is thousands of times lower than the density of water. And here we are in our metal, because I made it crystalline, and the same thing is likely to happen. So if we look at the surface of our metal, these atoms, which I've put near the top, are not the same as the ones below. So if we draw bonds on, then these ones near the top have an extra bond that is sticking out into nowhere. And it's worse than that, because this one here has got a bond that's sticking out here and a bond that's sticking out here, and if we imagine this is the end, there's also got one sticking out here. So there's a special atom at a corner where most of it is unhappy. It's not fully half, and this water is also not fully half because it's not right at the surface. It is slightly below because where the interface comes is a little bit difficult to tell. With metals, it's easier to think about it because we can imagine the electron C, which is the metallic bond, extends a little bit outside the atom. And so that's why I've drawn these nuclei being inside, and there's only one bond left over that is unhappy, that's not satisfied. But what happens in reality? In reality, we can't stay like that. That's a very high energy situation. We've cut those bonds and broken them, and we're in a bad situation. So something is bound to happen. The easiest thing to happen is that the atoms move around. Because we've got enough energy from these open bonds, we can do something simple. The simple thing would be, let me draw them bigger. Okay, here they are, bigger in crappy diagram form. The simple thing for them to do would be to interact with the neighbour in pairs. These ones can't interact because they've only got one electron each. It's a broken bond. If we're imagining it as being in a broken bond, then they would have one electron of the electron pair that was in the bond. Or if we're imagining it as a broken bond where one of the atoms gets both electrons, then every other one will have none. So if we consider them all to have one as radicals, then we've got one-armed arrows because that's how chemistry works. And we can draw this new situation, which goes to this new situation. And of course we can't stop there because we've generated a double bond, single bond situation, which means that half of the bonds are stronger than the others. They're not twice as strong, but they are much stronger. And so we have to shorten these to allow for it. As you can see, we now have rows of pairs of atoms, and if we did a measuring method on this surface, so if we imagine this to be silicon, for example, and we look at the surface of a silicon wafer in a vacuum so that nothing is sticking on the surface, then this is exactly what we would see. If we look in the bulk, we would see a crystal structure, and if we look on the surface, we would see a crystal structure which is different, and it has a periodicity. So the repeat pattern is twice as far apart as the bulk material. We can do this with X-ray, so if we look into the bulk with X-ray diffraction, which I think you've had in physics, if we look into the bulk with X-ray diffraction, we would get a diffraction pattern that would tell us how far apart these atoms are and allow us to deduce what the crystal structure is. The nicer the crystal, the easier it is. Then we can look at the surface with a low angle diffraction method. Can do it with low angle X-rays. Then it mostly looks at the surface. So we look at the reflections at the low angle. We send the X-rays in at the low angle and we fiddle with the power, so they mostly bounce off the surface. Then we get a different X-ray pattern, and that is of the surface, and that would tell us that these atoms, or this structure, has these features, and they're twice as far apart as the ones in here, but there are two atoms instead of one. This gives us a new structure that we can look at. We can also look at it with atomic force microscopy directly. What do we find? We find this distortion, but it isn't as bad as I've drawn it, because obviously this parallelogram here is under stress, and this other one is too. This one's bigger than it should be, and this one is smaller than it should be. So a bit of rearrangement goes on in the second level as well. These atoms can then reorganize to form a different structure where they move around to do something new. Obviously the ones where it's particularly stretched will move apart, and the ones where it's particularly compressed will move together, so that this weird corner isn't in there. That will again have a knock-on effect, and so we roll on through our material until we get to the bulk, which is about 5 or 6 layers down. It then starts behaving just like normal. But the surface layers are not normal. They're strained, they've got different gaps between the atoms to the rest of the material, and weird things are happening. What happens if we add some more material to the surface? So we add the same red stuff, whatever that is, red circles to it, then we see that it propagates. So effectively we add a new layer, and we can add to the top of this perfectly, but these ones will form this new structure. It doesn't have to be the same one, so it could form up here, and these ones relax slightly because now they're now the second layer. Effectively nothing is happening from a global energy perspective. We're really adding a bulk layer, but what's really happening is we're adding a new distorted rearranged layer, and all of the layers below are adjusting to take up their new properties as the second, third, fourth and fifth layer in the crystal. If we look at metals, we have the same thing. Now we can think about what happens if we add a different material to the surface. So I've put it to here to avoid the question of rearrangement to start with. And if we put on a material that would like to have bigger bonds, longer bonds, onto the surface, so we have to attach something like this onto it, this pin's going to die, then we end up with a mismatch. We have a mismatch between the structure with the preferred lengths of the bonds in this material to the preferred length of bonds in this material. So now we have two extreme possibilities that we can think of. In the first extreme possibility, the bottom material that's already existing bullies the second material that we attach and forces it to go into the crystal structure that the bottom material, this red one, wants. And in the other extreme possibility, the black ones go as they want and just ignore the bottom one, either bullying it or just going on top and not bonding to it, so just having this same structure just attached. What happens in reality? Obviously something in between. In reality, the first layer of this black material that we add will have to deal with this red crystal structure because it doesn't have any friends on the top helping it. And as you recall, the crystal structure near the surface propagates 5 layers into the surface. So likewise, a single layer of a new material, even if it's got very strong bonding, is going to be affected to a large extent by the underlying material. So now it will either accommodate or it will sit in a very low density pattern. Something weird will happen. Now let's rearrange it again. So we can see from our rearranged structure a little bit better than we could from the normal structure that if we add a few extra atoms to it, we can get some energy back. We can break these double bonds, so let's do that, and that will allow us to form one bond every 2 atoms. Let's do that. One bond every 2 atoms to a new one. That is going to be a difficult bond because it's going to be part of a bond, so we're going to have to form some kind of interaction with the other one too. But that will allow us to get back some of the energy, so this can now be arranged to straighten out some of these lines so that it gets back some of that energy that was hidden in the stress on these bonds. We can think of this as being like organic chemistry. So if we go back to organic chemistry and we look at different rings, we will recall probably that a hexagonal ring is very low in energy. They're quite common in nature. 6 rings are very common in nature, and that's because the normal angle of a carbon-carbon bond is very close to 120 degrees anyway. If we go down to a pentagon, pentagons are quite common in natural chemicals as well. that we don't have to deal with very much. So, or we don't have to deal with very much extra energy because the angle is actually slightly less than 120 degrees. So pentagons are nearly as favoured as hexagons, but not as much. It's closer to 120 than it is to whatever a pentagon is. If we go down further, however, we start to introduce a problem. Because obviously if we make a square, then we need 90 degrees at these corners, or that's at least the best way to divide it if they're all the same. Otherwise we can make one tighter and the other one's more open, but 90 degrees is considerably less than 120, and obviously if we have a triangle we'll end up with an equilateral triangle if we have the same bonds in there. So if these are all carbons we would have an equilateral triangle pretty much, and the angles would be around 60 degrees. We know this from the typical chemicals that we use. So if we take an epoxy adhesive is an epoxide, which is a chemical like this. So it's a chain, let's just draw one side. It's a chain with an oxygen on one corner of a three-membered ring. An epoxide is effectively an ether, but it's an ether that's reactive. If we take normal ether, so if we take diethyl ether for example, it's a solvent that we might use in the laboratory to clean things. It doesn't really react with anything. If we take an epoxide, we know from the name epoxy adhesive, it is reactive and it will attach to other things. So the epoxy group can be attacked from one end here, and it opens and it forms, breaks the ring up and forms a new compound. So we form a new bond here. Typically it's in an epoxy adhesive, it's an amide, so a nitrogen attacks from this end. The energy for that reaction comes from the strain in this bond, and this one doesn't do it at all. If we have a cyclic ether that is six-membered, it won't react very much at all. The epoxides are really reactive. So, sorry about the light black. If we resolve this one perfectly, we can imagine that this atom on the surface has a handy bond angle and length that fits exactly between these two. It's a two-dimensional representation. There's obviously nothing stopping it reacting in the other dimension as well if it's a real surface. And these atoms that we've added to the top can sit in between atoms of the surface, allowing the base material to relax. The ultimate version of this would be attaching hydrogens or fluorines, which only have one bond each, to the surface, which would enable something like silicon to relax back to its normal crystal structure, because we have now filled it all in. In chemistry, we like to call these dangling bonds. They're bonds just like the other possibilities, or just like a normal growing crystal. When our new material gets thicker, it will then start to do its own bulk thing and form its own crystal structure. So it's only the first layer, or possibly two, that are different. The other thing of interest while we're thinking about surfaces is how they grow. So if we take this material, which has got some kind of strange square crystal structure, if we add an atom to it, it has to add on here. I've obviously ignored the rearrangement for the purposes of this part. If we add an atom to it, this atom is obviously very high energy, and it is not very happy at all. If we add another atom to it, we can put it somewhere, but the lowest energy place to put it would be here, because it can fulfill its bonding a little bit better. So when it started, it had 3 bonds hanging out, and now it's only got 2, so we've now only got 4 shared between 2. If we think of it as the amount of non-fulfilled bonds per atom, the first one would have 3, and the second one only has 2, because we've got 2 each. If we add a third one, we have 2 each on the end ones and only 1 on the middle ones. So we've got 5 divided by 2, and so on. As I mentioned, in 3 and then 2 dimensions, so I'm doing a 2-dimensional representation of a 3D crystal, which gives me a 1-dimensional representation of a 2D surface, which reduces my dimensionality. But if I had this in this plane, I could also have a corner atom, which has even more, because I would have bonds coming out here and going down there. So the first one would have 5, and the second one would have less, would have 8, therefore. So these special atoms at the corners are more reactive than any of the other ones because they have more bonds that are not satisfied, so they can do more things. Obviously they are going to rearrange, so these bonds are going to react to form something. They will bond to other things, but it will be strained, so there will be a lot of energy available to react with things. So the 2 things that I want to mention here is the amount of energy that we get back per atom that we give goes up as we add more and more, and so it is obviously better energetically to add them to the edge of the growing island, as it's called. So if we grow an island on the surface, so we grow an extra layer, then it is energetically better, which is unsurprising because crystals actually form. If crystals didn't form, then they would just sort of form in a jumbled up way. But they grow across the surface in a single layer by layer fashion. The interesting thing about this is if we apply atoms at a constant rate or with a constant amount of energy, then we start again with that. If we apply atoms and they're coming in and they can leave again and they have a certain amount of energy, then the rate of deposition goes down every time we finish a layer for a little bit until we start the next one, because it requires more energy to start the next layer. It also goes up when we get close to finishing it because we're filling in those last few sites, and then it stops for a little bit and then it starts again. If we're applying them at constant rate, which I was trying to say, obviously they come at a constant rate, so that's different. This only applies, however, if the atoms can move around on the surface to find the island, because obviously an atom is blind. It doesn't know that there's an island over here, so it will have to wander around the surface to find it, which means that if we do this process at a high enough temperature, if it's from the gas phase, then it can move across the surface. If we do it by electrodeposition in a solution, we have to be close to the potential where the metal can dissolve again, or molecule, because then the molecules can go in and out of the surface until they find a lower energy spot, and then they stay there. The ones that stick out more will fall off, and the ones that stick in more will tend to stay. This gives us different types of crystal growth. But what I'm interested in at the moment is these different sites, because that is where catalysis will happen. If we have a molecule that comes along, it will either react preferentially with the really reactive sites on the outside corners, because those are the ones that have more bond energy, or it will snuggle down on the inside corners because then it can interact with more atoms. It depends on the species that we're going to interact, but what it very seldom does is glom onto the surface, which is flat. It is much more likely to interact with these interesting sites. So if we're trying to make a catalyst, one of the challenges is often how do we make the most of these sites, depending on which type of catalyst we want to do, depending on what reaction we're interested in, how big the molecule is, and how it interacts with the surface. So as a last thing for today, I think we will just let some air into our vacuum. So if we take this and we allow some air to come into this chamber, then we can satisfy these dangling bonds, which are effectively all radicals, so they're really, really reactive. We can satisfy these dangling bonds, hang on, there's one on here too, with some other material. So if we bring along some hydrogen, for example, it will sit on here and make these happy. But hydrogen is not always present, and it's not really the first thing that you think of if you're going to let some air in. So what else could be there? We could put, obviously, fluorine on there instead of hydrogen, but that's not much less rare. So let's put some water on. So if we put some water on, the water is now unhappy because we've got radicals still, but we can get rid of a hydrogen, so an H+, or we can put a hydrogen onto the next atom, so we can generate an OH, which is also a nice finishing group. It finishes off because the OH only has one connection. Because if we put oxygen on there, then the oxygen would tend to have a double bond, and the double bond has got to be with something. Or we could have oxygen as a molecular species, so the oxygen has interacted with the surface, but now our plus or our radical is still on this end of the oxygen, so it's still reactive, it's still going to do something. If this is a metal or silicon, then it will react further. So when we leave it in the air for a bit longer, let us make a layer, we will end up with a layer at the surface of a different compound, which has a different crystal structure, which would be the oxide. So if we take silicon, for example, we take our silicon wafer and we just leave it in the air, we will end up with silicon dioxide on the surface, and the silicon dioxide has a different shape and a different crystal structure than the material below. So now we're going to have the same problem that we had earlier. We've got a mismatch between the two lattices. This one is going to be probably bigger, but also possibly not the same shape. And so there will be some kind of stress at this interface where some of them are happier than others, so the odd one will connect really well, and some of the others will not. Then we will have probably something at the upper surface, which will be very similar to what we just had. So we would have our wafer now looking like this. We would have our silicon, then we have a thin layer of SiO2, and then at the surface of it we will have another layer, which would be SiOH, at least the bonds, just to cap off the top so that we don't have bonds sticking out, because chemistry doesn't like bonds that stick out, and if we've got a reactive medium like air, something will happen eventually. There are atoms and molecules hitting the surface all the time, so typically it is less than a second in a normal air pressure for the surface to have been hit, for every atom to have been hit by something. If it's a silicon wafer, it will be hit by water, air, water, nitrogen, oxygen, and eventually we will find some kind of mostly oxide on the surface. We might get some nitrides, but mostly oxide and a bit of hydroxide right at the top. The hydroxide can't decompose to silicon oxide because of the shape. But now we've got a new problem, which is the redox parameters of this stack, because the silicon is obviously in its reduced state, it's silicon 0, the silicon dioxide is in the +2 state, and the silicon hydroxide is also in the +2 state. So those are really reasonably heavy to interact, but the silicon 0 has a different electrical potential to the dioxide. So now we are going to generate a little bit of stress effectively, and if we think of it as from a thermodynamic point of view, the idea of having a perfect crystal, another perfect crystal, and a third perfect crystal on top is nice, but it's not what we would expect to see. We would expect to see some kind of mixing. So we would expect to see this layer near the bottom of the silicon to have more silicon 0 in it than it should have, to have missing oxygens effectively, and the bit near the top to have maybe a little bit too much, depending on what is outside. We will continue on this next time, but I had better stop there, I think, for one time.